mentioned this the other day, differentiability, great word. To actually be able to differentiate something at the particular point you're differentiating, the curve needs to be what we call smooth, continuous. Because remember, what we're basically finding is the equation of the tangent at that point. So if it doesn't exist that point, well, you can't draw a tangent in. And if it's not smooth, you're not going to get the same tangent, because you can't, like an absolute value curve. Well, hang on, where do I draw the tangent at that V point? Now, the sort of question you'd get on differentiability is they'd have the function, hopefully a picture, if not, hopefully you know what the picture looks like, and they might say, are there any points where this curve is not differentiable? And you're just looking for things like that. You're looking for gaps in the domain, sharp points, just finding where it's not a nice, neat, smooth curve. The formal definition, which you don't have to worry about, but formally what we're saying is, well, the derivative when we approach from the left-hand side would be the same as the derivative from the right-hand side. So in other words, the slope of the tangent as you come from the left-hand side would be the same as from the right-hand side. So there's the absolute value curve that I was talking about. And it's fine everywhere except at x equals 1, the sharp point. Can't be differentiated there, because on the left-hand side, well, if I was to draw a tangent on the left-hand side, I'd get a slope of -1. But if I was to draw it at the right-hand side, I'd get a slope of +1. So they're not the same. So formally that's why, but as I say, all we need to know is, oh look, it's a sharp point, I can't differentiate there. Whereas say a parabola, which is nice and smooth everywhere, and it's continuous everywhere, we don't have a problem with. We can differentiate that anywhere. So again, if I pick x equals 1, it doesn't matter whether I approach it from the left-hand side or the right-hand side, I'm going to end up with the same tangent. Okay, that's enough said about differentiability. So as I say, all we need to know is, oh look, there's a sharp point. Implicit differentiation. We love to call the same thing different things, to make it sound a bit more complicated, I suppose. But the chain rule, rates of change, derivatives, implicit differentiation, it's really all the same thing. Now, technically, implicit differentiation is in the Extension 2 course. But you've seen it already. We just didn't call it implicit differentiation. We called it rates of change yesterday. Essentially the same idea. Because there you go. There's our definition for implicit differentiation. Looks familiar? It's the same idea, that we can build a derivative using other derivatives. What it allows me to do, though, and where it's really useful, is, okay, we're trying to find the slope of a tangent at a particular point. Now, if it's a function, that's fantastic. It'll work beautifully. If it's not a function, we've got a problem. X equals y squared. It's not a function. It's a parabola on its side. So it's not going to work. Because if I pick an x value, there's two possible y values. And depending on which y value I pick, the slope's going to be different. So what we would have to do is make y the subject and differentiate that. But using implicit differentiation, we don't have to do that. And again, what is implicit differentiation, I hear you ask? It's exactly what we've been doing. Well, I said if we treat this like an equation, and all I'm saying is I'm going to differentiate both sides with respect to x. Oh, differentiate x with respect to x, that's not a problem. That's 1. Differentiating y squared with respect to x, okay, that's hard. So I don't do it. But what I make use of is our chain rule, our rates of change idea, call it whatever you like, is to say, I'm going to differentiate it with respect to y, because I can do that. And then I'll multiply it by dy dx. And if you have a look down here in that little oval, the dy's would cancel, and in fact I get the same as d dx of y squared. So now I'll look at this one, and on the right hand side I'll say, okay, differentiate y squared, can't do it with respect to x, but I can with respect to y. So it'll be 2y, but then times dy dx. But now I can rearrange this, and I've got a formula for the derivative. The difference with this formula, I don't substitute in the x value, I substitute in the y value. Now think back to what the function, well, it's not a function, think back to what the relation was. It's a parabola on its side. When I substituted in the x value, I had a problem, because there were two particular y values. But if I substitute in the y value, I don't have a problem, because there is only one point that it could be. So if I had said, we're going to differentiate x squared y cubed with respect to x, well, it's a product rule, because I've got two things multiplied together, x squared and I've got y cubed. So I write down the first, x squared. I differentiate the second. Well, hang on, y cubed. I can't differentiate that with respect to x, so I'll differentiate it with respect to y. And that'll be 3y squared, but then to balance it out, I'll multiply by dy dx. You're basically multiplying by whatever you differentiated with respect to y over what the question actually wants, dx. Okay, plus, write down the second, y cubed, diff the first, well, x squared, that's not a problem, that's 2x. And we end up with this beautiful expression there for the derivative. So if I wanted to find the equation of a tangent to a circle, now a circle is a problem because it's not a function. Okay, I could rearrange it, make y the subject, work out whether I'm talking about the top half of the circle or the bottom half of the circle, which would then be a function, and use that. Implicit differentiation is just quicker. Because I now say, well, x squared plus y squared equals 9. I am now going to differentiate both sides with respect to x. Differentiate x squared, 2x, not a problem. Differentiate y squared. Can't do that with respect to x, but I can with respect to y. So 2y, but times dy dx. And then on the right hand side, differentiate 9, well, that's just going to be 0. Rearrange it, and eventually there's our slope, minus x on y. So in order to find the slope for this particular curve, the circle, I need both the x and the y value. Well, again, have a look at the shape. It's a circle. If I just use an x value, 2 possible points. If I just use a y value, 2 possible points. But if I use both the x and the y value, it narrows it down to 1 point. So now I can find the slope at that particular point. So we want at the point 1, 2 root 2. So we substitute 1 in for x, 2 root 2 in for y. There's our slope. Point slope formula. And we end up with, eventually, there we go, our equation of the tangent. Without having to rearrange the original equation. So that's one of the advantages of implicit, what we call implicit differentiation. We'll just have a look at a couple of those. But as I say, it's actually in the Extension 2 course, not the Extension 1 course. However, it's still a handy idea to know.